Okay, now let's imagine doing the following experiment. In this container, we're going to seal it, and we're going to place in this container liquid A. And in a second sealed container, we'll stick liquid B, which is a different liquid. And we're going to run the same experiment. We're going to look at the pressure inside each container over time. And what we see with liquid A is we see a vapor pressure build up like this. So this would be the trace for liquid A. And for liquid B, we're going to see a trace that looks like this. So we see that liquid B has a greater vapor pressure. So this has a vapor pressure that's high, and liquid A has a vapor pressure that's low. And so drawing molecules in the gas phase as dots, we would imagine that liquid A is going to have maybe that many dots to represent the gas molecules that have entered the gas phase. And for liquid B, we of course would expect more gas molecules in the headspace of the container, giving it a higher vapor pressure. And so the question is, which of these two substances are the molecules more strongly attracted? In other words, are the intermolecular forces that make up liquid A, are those greater than the intermolecular forces that make up liquid B? Or is it the case that the intermolecular forces of the molecules that make up liquid B are those greater than the intermolecular forces of the molecules that make up liquid A? Which of these is correct? Well, remember, to enter the gas phase, you need to separate molecules. So if you easily enter the gas phase, you have a high vapor pressure, right? If you easily enter the gas phase, you have a high vapor pressure, but your intermolecular forces are therefore low because it's easy to separate them. So we see that high vapor pressure corresponds to low intermolecular forces. And of course, the converse is true. Low vapor pressure over here, that's going to correspond to high intermolecular forces. The molecules that make up liquid A, those tend to want to stay together, and therefore not as much of the molecules that make up A are going to enter the liquid phase. Now, the concept of vapor pressure is going to allow us to gain some insight into what is known as the normal boiling point of a liquid. And this kind of makes sense here. Basically, a liquid's going to boil when the vapor pressure of the liquid exceeds the atmospheric pressure. So the normal boiling point is when the vapor pressure of a liquid exceeds atmospheric pressure. And I'm just going to write air pressure. When this happens, you get boiling to occur. So let's see if we can answer the questions below. What is the normal boiling point of each liquid? Which liquid has the strongest intermolecular forces? And what type of intermolecular forces might each molecule display? So first to the boiling point of each liquid. Remember, the boiling point is when the vapor pressure of the liquid exceeds atmospheric pressure. And we know atmospheric pressure is 1 atmosphere. So for ethanol, we look at 1 atmosphere. We draw a line straight across, and we notice that at 1 atmosphere, that is the vapor pressure of ethanol at roughly 80 degrees Celsius, if we see where those 2 points meet. And therefore, we know anytime we get above roughly 80 degrees Celsius, the vapor pressure of the ethanol is going to exceed 1 atmosphere. So that means the boiling point of ethanol is roughly 80 degrees Celsius. If we do the same trick for water, 1 atmosphere, anytime the vapor pressure of water exceeds 1 atmosphere, it's going to boil. And we see that that occurs, 1 atmosphere pressure for water occurs at 100 degrees Celsius. You get above that, the vapor pressure is going to exceed the atmospheric pressure of 1 atmosphere, and the thing's going to boil. So you see easily that the boiling point of water is 100 degrees Celsius. You should be able to figure it out for octane, what its boiling point is, but on this graph you should notice that you cannot figure out what the boiling point of ethylene glycol is. Now, between these 4 liquids, which has the strongest intermolecular forces? If we remember that intermolecular forces are stronger with liquids with low vapor pressure, then it's pretty obvious that ethylene glycol of these 4 liquids is going to have the strongest of the intermolecular forces. Which type of intermolecular forces does each molecule display? Well, if we look at octane, that only has carbon and hydrogen in it. It's that large molecule at the top of the black line. And if a molecule only has carbon and hydrogen in it, it's generally nonpolar. And nonpolar molecules can only display induced dipole forces, London dispersion forces, van der Waals forces. So that's it. That's all it can display. The other molecules, they all have OH groups, which are going to allow them to hydrogen bond. Those OH groups are also going to induce a dipole in those molecules, and so those molecules can display dipole-dipole forces as well. Okay, to wrap up our study of vapor pressure, we're going to try this particular problem. We're going to imagine that 50 grams of water is sealed in a 1,000 liter container at 20 degrees Celsius. And we're going to ask ourselves, does all the water evaporate? If not, how much water remains in the liquid phase? We're given the vapor pressure of water at 20 degrees Celsius, 17.5 millimeters of mercury. Let's try to picture this here a little bit. I've got a sealed container. We know its volume, which is 1,000 liters. We know we're at 20 degrees Celsius. And we know we have some liquid in here, 50 grams of liquid water. And since it's sealed, we know some of that water is going to evaporate and enter the gas phase. Well, does all of it evaporate or just a portion of it? And how can we figure this out? Well, we're at 20 C, so we know the pressure of water that's going to be able to exist in this container. Remember, the pressure is only going to build up until we hit 17.5 millimeters of mercury. We know that's going to happen. So we can know what the pressure is. We know the volume of this container. We know the temperature of the container. We also know the gas constant. So the only thing we don't know is the moles of gas. The only thing we don't know, I should say, if we're thinking of the ideal gas law, the only thing we don't know is how many moles of water are going to evaporate to give us this pressure, which is pretty much what this question's asking, right? Will all 50 grams evaporate, or will it only be a portion of that? So we're going to use this equation to find the moles of gas that are going to evaporate into the container. And from that, we can get the grams of water. If it's 50 grams or more, then, of course, all the water is going to evaporate. If it's less than 50 grams, let's say only 20 grams will give us this pressure, then we know that 20 grams of the water evaporated and 30 grams will be left behind. 50 minus 20 is 30. So let's remind ourselves of what we're going to need our units in if we're going to use this equation. Because, you know, if we want moles, which is what we're looking for, we just divide both sides of this equation by RT. And our moles, which we're looking for, is going to be PV over RT. So let's see. R, we're going to remember, is 0.0821 liter atmosphere per mole per Kelvin. It looks like I've got my container size in liters, and that's a good thing. I don't have my pressure in atmospheres. So let's do that conversion. And we also notice that we don't have our temperature in kelvins. So we're also going to do that conversion. So if I have 17.5 millimeters of mercury, that's how much would be able to evaporate to that pressure. We remember that there are 760 millimeters of mercury in an atmosphere. 17.5 divided by 760, 0.023 atmospheres. And then for our Kelvin, we're just going to add 273 to 20, and our Kelvin temperature is going to be 293 Kelvin. That gets us everything we need, right? We have our pressure, 0.023 atmospheres. We have our volume, which is 1,000 liters. We have R, which is 0.0821. I'm going to put the units, well, let's see if I can fit them in here. Liter, atmosphere, per mole, per Kelvin. I'm sorry, I'm squeezing that in there. And then we're also going to divide by 293 Kelvin. Atmosphere will cancel atmosphere. Liter will cancel liter. Inverse Kelvin on the denominator cancels inverse Kelvin on the denominator. We have inverse mole on the denominator, which is a mole, which is what we're looking for. So we know that our moles is going to be whatever this calculation comes out to. Let's do the arithmetic. So I take 0.023, I multiply by 1,000, I divide by 0.0821, and I'm also going to divide by 293. We're going to get 0.96 moles of water. That's not quite 50 grams. How many grams is it? Well, if you remember, 1 mole of water is 18 grams of water. So I'd take my 0.95, I multiply by 18. That's going to be 17.2 grams of water, roughly 17 grams. And we remember that we have 50 grams in the container. 17 are going to evaporate. So 50 minus 17, that's going to give me 33 grams of water. That's going to remain in the liquid phase, and 17 grams of water that's going to vaporize.